Good morning, dear students. Can you hear me?
Uh-huh.
Yeah, we can.
Okay. So let's begin. Today we shall go abstract and consider so-called sets. I'm sure that you are familiar with that concept. That is, set is something like a collection or I don't know, grouping or whatever of various objects. Of course, this log idea does not comprise any strict definition. What is a set? If it is a collection, and what is a collection? In fact, it is quite hard to define sets if we want that sets are the most basic notion of mathematics, because every notion, if you define it, generally you define it on the base of some previous notions, and clearly the most basic notion cannot be defined as I don't know, a dog is an animal such that, because what is an animal? A set is a mathematical object such that. So as it is hardly possible to define sets this way, we shall practice so-called axiomatic approach, axiomatic method. We have already seen it, once we talked about strings, and we have and we said that this empty brackets is string, and for whatever string s, you may somehow join it with a new element. So this way, our symbols, empty brackets and column, were primitive. They had no definition. Of course, later we interpreted this symbol as the empty string. But what is the empty string? Just nothing, just some object we consider to be a string in the definition. Likewise, we want to define sets. So we don't want to say what a set is, but how sets behave. So we want to specify some rules on how sets behave. What does it mean, behave? Behave, that means that one set somehow relates to another one. First of all, let's indeed think about sets as some basics for mathematics. So we will assume that everything is a set. Of course, that's not axiom, but some philosophical postulate. So everything is a set. So every mathematical object might be thought of as a set of some special form. Why this postulate is important? Because it allows us to provide some uniform foundations for mathematics. So mathematics will thus have a unified object. So it is so this way mathematics just deals with sets of various forms, nothing else. So what is the object of mathematics? You may think that it is numbers or some figures of the plane and so on, and many other kinds of things. But now, abstractly, we may think that sets uh, comprise the object of mathematics. So everything is a set. Every figure on the plane is modeled as a set. So whatever its nature initially be, we initially is, we will model it as a set. So if we have say plane, this is a set. If we have a number, say a pi, a real number, it is a set. And the set of all real numbers is another set. If you have a natural number, say 4, it is still a set. So of course, it this might scare you. So every natural number is a set. But this step is quite logical. If we want to model every object of mathematics as a set of some special form. By the way, in this course, we are not going to define which set, say, 4 is or pi is. But by the way, let's think of these objects as sets of some special form. Okay, so I have promised to impose some rules on how sets do behave. What does it mean that one set behaves some way? We shall say that one set may be element, an element of another one. One set may be an element of another set. What does it mean to be an element? Of course, intuitively, that means that one object uh, is a part, a member of some collection. So, a ball A uh, might be found in a box B. So it is in a box B. But of course, this intuitive idea of elementhood of being an element, it is flawed, in fact. It is not quite accurate. So we don't say what doesn't mean that one set is an element of another set, but rather we will impose some rules on this relation. So X is an element of Y. X is an element of Y. Or another way to read it, X belongs to Y. Isn't it too abstract so far?
No.
Mm,
So I think it is still quite clear. So one set may be an element of another one. Everything is a set. So far, so good. Of course, in most mathematical applications, and in fact, most mathematical theories, we use equality as our basic relation. What does it mean? That one object is equal to some other object. In set theory, we may do either of two things. We may think of equality as of a primitive relation. So we may think that one set might be equal to another one, and equality is something we don't want to define. But another way is the other way is that we think we try to define equality in terms of elementhood. We shall take the second approach. So, a definition. We say that a set A is equal to a set B if and only if for every set X, X is an element of A, if and only if X is an element of B. So, two sets are equal by definition if and only if the elements are the same, if they consist of the same elements. So do you have a question? So please. Or if you have no question, please switch your microphone off. So thank you. We say that two sets are equal if and only if they have the same elements. And another definition close to this one is set inclusion, or being a subset. We say that A is included in B, or otherwise we may put it the following way: A is a subset, is a subset, is a subset of B, and we shall use such a symbol. A is a subset of B if and only if for each X, if X is an element of A, then X is an element of B. That is, every element of A is an element of B. Do you remember our earlier tries to formalize our natural language when we said something like every rose is a plant, every oak is a tree? Do you remember it? Our first lectures, our first seminars.
Yes.
Yes.
Then we used exactly such a construction. How is it possible to say that every A is B? For each X, if X is A, then X is B. Here we have exactly that. Schematically, of course, you may make a diagram, a well-known Euler's diagram, which make this notion of set inclusion more vivid. So A is a part of B. The collection A is a part of the collection B. Every element from A is an element of B. Dear students, please remember that everything is a set in our model. So X is also a set. There is no such a category as elements, which are not sets. Everything is a set, and all quantifiers are over sets. That means that the domain of all our predicates is the realm of sets. Okay. Using logic, we can easily prove some simple statements about these two relations. First of all, let's study set inclusion. I say that for each ABC, for each sets ABC, A is a subset of A. Why is it so? Easily, we may notice that if X is an element of A, then X is an element of A. Here we have two identical statements as the assumption and the conclusion of an implication. And this implication is always true for logical reasons. For if X is not an element, then the assumption is false, hence it is true. Or otherwise, X is an element, and in this implication, the conclusion is true, hence the implication is true as well. Because it is quite clear. What else? If A is a subset of B and B is a subset of C, then what?
A is a
Then
subset
it-
of C.
Of course. Should I prove it explicitly or is it clear?
Probably clear.
It should be clear from this definition. If X belongs to A, then X belongs to B. That's given. And also, if X belongs to B, then X belongs to C for whatever X. Then, considering an arbitrary X and assuming that is an element of A, you first conclude that X belongs to B and then that X belongs to C. Also, A is equal to B when? If and only if A is a subset of B and B is a subset of A. Why is it so? Because this, by implication, this logical equivalence, we know that alpha is equivalent to beta when, if and only if, this one is true. Alpha implies beta and beta implies alpha. Is it clear?
Yes.
And now what about equality? Clearly, every set is equal to itself. If F is equal to B and B is equal to C, then A equals C. And the last one, if A is equal to B, then B is equal to A. All these facts are easy theorems. They are not by definition, they are not intuitively obvious, so they are, but we don't prove them this way. We infer these facts directly from our definitions. And of course, lemma 2 might be proved using lemma 1. For example, here we can say that that's given that A is a subset of B and B is a subset of C. This follows from this third statement, and then A is a subset of C. Likewise, we may prove that C is a subset of A and apply this statement for the other direction and then obtain that A equals C. Is it clear?
Yeah.
I have a question about the third one. Shouldn't the implication be to the other side, as well?
Where? Here.
In the third one.
This
Yes.
one.
Yes.
In fact, it's possible to have a by implication, but there is no need in that. Why? You just see, this is for all A and B. Just rename B to A and A to B, and then you shall obtain the same. So
Yes.
one implication is enough.
Okay,
If it
thank
is
you.
for all A and B, it's a very easy but useful trick. But still useful trick. What else? By definition, dear students, remember that we are playing some formal game. We don't use our intuition of sets as some collections and so on. Because this way, of course, all the statements are evident, but some harder statements, some more complicated statements would not be that evident. But we want to devise some formal rules which would allow us to consider both complicated statements and easy statements in one unified formalism based solely on logic. Okay. You know that by definition, two sets are equal if and only if they have the same elements. So their elements are the same. Every set is, one may say, uniquely determined by its elements. If you have provided some elements, you may uniquely define a set. But what if we think about the following? Assume that A equals B, and A is an element of C. Does it imply that B is also an element of C? What do you think about it?
Yes.
But how is it possible to prove it? By definition, we see that A and B has the same elements. So every x, if x is an element of A, then x is an element of B and vice versa. A is an element of C. Why B is an element of C?
Because, well, for each x, if x is an element of A, it's an element of C.
Why? So you think that if x is an element of y and y is an element of z,
No, it's
then x is an element of z. No way. No way. Being an element is not a transitive relation. No, element of my element is not my
yes,
element in general.
It's not about it. It's about like may I write it like over here?
So please.
X is an element of A implies. Oh, sorry. Implies X is an element of C. It's by definition. So.
Why? This would mean that A is a
I see that.
subset
I
of
see
C.
that.
It
Yes.
is not a subset,
Yes.
just
Yes.
an
Yes.
element.
Sorry.
In fact, there is no way to prove it, but it is intuitively clear. We want that equal sets behave identically. So if we can't prove it, but we want it, we have to just take it as an axiom. So this is our first explicitly set axiom. We say we shall call it the axiom of equality. The axiom of equality. It says that for every sets A, B, C, if A equals B and A is an element of C, then B is an element of C as well. So we know that this is an axiom, and conversely, if C is an element of A and A equals B, then C is an element of B just by the definition of equality. So we see that equal sets behave the same way on the both sides of this elementhood sign. So taken together, these two statements give rise to the following principle. which might be proved, but we just don't have enough formal developments in order to do that. So let's call it the substitution principle. Substitution principle. We shall use it freely. If phi is a property, defined just in terms of elementhood, so it is a set theoretic property, then from A being equal to B, it follows that phi of A takes place if and only if phi of B holds. So for every property, two equal sets behave the same way. Is it clear? I think it is very appealing intuitively. It is quite clear, isn't it?
Yeah, it is.
So we shall use it freely. We shall freely substitute one set for any set equal to it. Another axiom. We have said that everything is a set. So an element of a set is a set. If y is an element of x, it is another set. If z is an element of y, it is another set. And is it possible to continue this chain, this sequence, decreasing in our elementhood relation? Is it possible to continue it indefinitely, to continue it infinitely?
No,
No, but why?
because there should be
Yeah.
a list element.
Why?
Like, okay.
Because you want it. Because you want it. So this is another axiom. It is called the axiom of foundation. Intuitively, it is not possible to take a box from a box, then a box from that in a box, and so on infinitely. But what about mathematics? So in mathematics, we shall imply the following axiom of foundation. The axiom of foundation says the following thing. There is no sequence, infinite sequence. Of course, there is more precise form for that axiom, but let's be happy with this one. There is no infinite sequences like x0, x1, x2. Okay, this might scare some of you. But the main idea is that it is infinite to the left. And so on. Such sequences are explicitly forbidden. Is it clear?
Yes.
Let's have
Not quite. If x0 is a set of all natural numbers, then
if n is a set of all natural numbers, and this is a set of all natural numbers except 0, this is a set of all natural numbers except 0 and
yes,
1,
like that.
and so on. Dear students, here we have inclusion, and here we have
Okay,
element
yes.
code. These are distinct, and this
Making the same
distinction,
mistake twice.
this distinction, you are not alone. Many mathematicians of the past in 19th century were not that sure what what the difference between these two is, because this difference is abstract. So this one is, of course, defined in terms of this one, but this relation is not very intuitive, in fact. As a corollary, we may obtain the following. There is no set x such that x is an element of x. Why? The proof is very easy. If x would be an element of x, if x be an element of x, then 1 would easily construct such an infinite sequence. Is it clear? Dear students,
Yes.
Yes, it's clear.
we may take all x's be the same. X0 might be equal to x1, x2, and so on. Here we have no indication that they must be distinct from each other. And you know, according to the old adage by George Cantor, one of the pioneers of mathematical logic and in particular set theory, that the essence of mathematics lies in its freedom. So in mathematics, if everything was not explicitly forbidden and it is not contradictive, then it is possible. And another corollary of this kind is the following one. It is not possible that x is an element of y, where y is an element of x. Clearly, otherwise, we would be able to construct such an infinite sequence. Is it clear?
Yes.
This principle, and especially its corollaries of this form, are very clear intuitively. If you think of a set as of a collection of some objects, as a box containing some objects, some other boxes, of course, it is not possible that your box is stored in itself. It's not possible intuitively. So this principle is also quite natural. But this principle is negative. It says that something is not possible. But what about positive principles? Let's consider some principles that allow us to construct new sets. We shall call them set construction principles. It is another bunch of axioms. The first one, we may codename it as, you know, the American motto, out of many, one. A pluribus unum, you know. This is the caption at the United States state seal with the eagle and so on, out of many one. So what is the main idea? The main idea is that if you have one or two or more, that is a finite number of sets, you may just group them together in order to construct a new set, which is comprised of exactly this one. So let A1 and so on AN be some sets. Then there exists a set which is denoted the following way. I shall use this curly brackets as set denoted this way, such that for every x is an element of this set, if and only if x either equals 1 or it equals a2 and so on. Is it clear?
Yes, it's clear.
So I may explicitly group one or more sets together. Let's see some examples. We shall assume that some sets in fact exist. Assume that at least one set exists. Say the set of natural numbers. And that means, of course, that the natural numbers also exist, and they are sets of some kind. So we may, for example, group 2 and 3 together. What does it mean that x is an element of this set? That means that x equals 2 or x equals 3. And this holds for every x. Is it clear?
Yes, it's clear.
By the way, what do you think about these sets? This one and say this one. Are they distinct or the same?
Probably the same.
The
because
same.
well, any
By definition of equality, they are the same.
Well, they are equal. Why is it so? So these are just two names. These are just two synonyms. Two names for the same set. Two synonyms. Why is it so? Let's prove it. You know, two sets are equal if and only if for each x is an element of A, if and only if x is an element of B. Let's prove it. Consider some arbitrary, let's consider an arbitrary x. So what does it mean that x is an element of this set? This just means that x equals 3 or x equals 2 or x equals no, of this one. Do you agree?
yes, and well,
And what does it mean that x is an element of this set? That means that x either equals 2 or equals 3. Ha! But clearly these two statements are logically equivalent. Hence our sets are equal. That's it. So this notation does not allow us to say anything about the order of objects or their multiplicity. So how many copies of 3 do we have here? Either object, either element is either belongs any element either belongs to a set or does not. So we cannot say that it belongs to our set twice. This makes no sense. Is it clear?
Yes.
Yes.
Another interesting application is so-called singleton. In mathematics, we like various degenerate cases. And what if here we take just one set? What if we take just one set? We may consider the following set, which is called the singleton of A. The singleton of A. And what can we say about it? X is an element of that singleton if and only if X equals A. What is the difference between this singleton and A itself? It is quite clear, quite hard to grasp it intuitively. Of course, if you have two objects, the set comprising both of them is intuitively distinct from either. But what if you want to consider the set that consists of just one object? Wouldn't be it natural to identify this set and A? In some context, it is natural, but in order to formally construct our set theory, we have to make a distinction between A and the singleton of A. And this distinction being quite hard to grasp intuitively is in fact of fundamental importance. Is it clear?
Yes.
So if you may have groupings of 2, 3, or 4 objects of 2 or 3 sets, it's formally natural to assume that you may group just one object and obtain a set of just one element, which is still distinct from that element corollary. No A is an element of no A is equal to its singleton. Why is it so? The proof is really easy. A is an element of the singleton. Why is it so? This is by definition. If you take A for X, you shall obtain something like that. A is an element of the singleton if A equals A, but we know that this is true. Hence, the left-hand side must be true as well. Is it clear?
Yes.
So A is an element of A, of course, by definition. If A be equal to its singleton, then you know equal sets behave identically, then we would obtain this thing. A would be an element of A, which is not possible. It would be a contradiction. Is it clear?
So far.
Okay.
Oh, we will prove it.
We have proved it, in fact. Okay.
So can you please repeat what is singleton?
The singleton is just the set of this form. The set whose only element is A. It is a singleton of A. One element set.
So
Okay.
it has only one element.
Of course. Of course. Of course, but what does it mean? Only one element. In fact, you implicitly define this notion using this formalism. You say that let's take n being equal 1. X is an element of this set if and only if X is just A1. So this is a case of this general concept. So another way to construct a new set is so-called subset specification. What is it? It's also quite natural. Let phi of x be a property or predicate over sets. And A be a set. Then there exists a set which is denoted in the following way. All x's x, it is read the following way. All x's from A which satisfy phi, such that for every y is an element of this set if and only if y is an element of A and y satisfies phi. By the way, this construction is called the set builder notation. Let's see some examples. We have assumed that there is a set of all naturals. And we may, for example, take all naturals which are even. Or, for example, all naturals such that there exists some natural y, so that x equals y squared. The set of all full squares. Is it clear?
Yes, but
As a corollary, we may obtain that the set of all x's from A who satisfy phi is a subset of A. So we have specified a subset by some property. You just take all elements from some predefined A which satisfy some property. Is it clear?
Now it's clear.
And now let's use it to provide some degenerate example. What if phi holds for no sets. What if phi is contradictive? By definition, we let this symbol, which we shall later use for null or void or empty set, let's define it the following way. The set of all natural numbers which are not equal to itself, which is not equal to itself. Let's group together all naturals which don't equal itself themselves. That's better. So what can one say about this set?
Why natural numbers?
Because the set of all natural numbers already exists. We have assumed that. It is not. It's not important which set we take here, but we shall take some set, whatever. Why not naturals? By definition, a set E is empty. A set E is empty if for each x is not an element of E. So an empty set is a set without elements. Is it clear?
Yes.
Clearly, this set is empty. Why is it so? Indeed, if x were an element of this set, then x is not equal to itself, but every set is equal to itself. So this is not possible. If x is an element of this set, then we have got a contradiction. That means that for each x, this is false. You may infer a falsity only from a falsity. So for each x, this is false. For each x is not an element of this set. So this set is empty. Is it clear? Dear students,
Yes, it's clear.
let's prove that this set is the only empty set. Lemma. If E is empty, then for every set A, E is a subset of A. So the empty set is a subset of any set. This is, by the way, the same idea that our principle, our statement about the present king of France. So it is the same. The present king of France is bold. The set of present kings of France is a subset of the set of all bold people. Let's prove it, for it is very easy. What does it mean that let's take some E, some A. What does it mean that E is a subset of A? By definition, that means that for every X, if X is an element of E, then X is an element of A. Do you agree?
Yeah.
Yes.
Mm.
This is just by definition, but this is false. This is false. Why is it so? Because by definition, we have no element in an empty set. So this is false. And from falsity, it follows what? It follows everything. So the implication is true. Hence, I see that all this thing is true, whence this one is true as well. So an empty set is a subset of any set. Corollary. If E is empty, then E equals our this set. Then E equals this set. The proof is very easy. E is empty. We know that any empty set is that empty set is a subset of any set. This is by our lemma. I don't know. Let it be lemma 5. E is empty, so it is a subset of our echelon empty set of this one. This one is empty. That means by the same lemma that it is a subset of any set. So empty set is a subset of any set. Ha! But if we come back to lemma 1, if we can, come back to lemma 1, we may see that one set is a one set equals another one if and only if each set is A equals B if and only if A is a subset of B and B is a subset of A. So here we have exactly such a situation. So by lemma 1, that means that E equals our set. So what is the conclusion? We may say that there is a unique empty set, and this set is the empty set. It is unique. There is just one empty set. Every two empty sets are equal to each other. So this one is the empty set. Not an empty set, but the empty set. Is it clear?
Yeah.
Mm-hmm. Okay. And now another set construction principle is the set of all subsets, or as they call it, the power set. The power set. Okay, if A is a set, then there exists a set P of A, such that for each X is an element of P of A if and only if X is a subset of A. So you may just group all subsets of any set together. By the way, let's see some examples. Which are the subsets of empty set? Does it have any?
No, there are none.
Why? You know. Empty set is a subset of any set. And for each A, by the way, A is a subset of A. So this set cannot be empty. So that's not empty. The power set, it is called the power set when the letter P. The power set cannot be empty. So it has at least one element, the empty set itself. What else? Can it have any other element?
No.
No, why? If X is an element of this set, then by definition, X is a subset of the empty set. That means that every element of X is an element of the empty set, but it has, the later set has no element, so it is false. This is false. And if where from can one infer falsity? Only from a falsity. If from some statement it follows a falsity, then that statement itself is false. So that's false for every Y. Hence, Y has no element that it is empty. So if, or one may put it in the following form. So Y is an element of this set. Every subset of no, not Y is empty, but X is empty. Every subset of the empty set is empty itself. So this is a subset of the singleton, and the converse inclusion is trivial. Is it clear?
Yes.
And what are the subsets of this set, by the way? What are the subsets of singleton, of any singleton, by the way?
An empty set?
The empty set, it is unique. And what else?
A.
Mm-hmm. And what if you take a two-element set? Still the empty set, still this set itself, and what else?
These two elements.
Not two elements, but they're singletons.
Yeah.
By the way, how many elements in formula do you have here? 0. And there?
1.
1. And 2 to the power 0 equals 1. How many elements here?
1.
And here?
2.
2 to the power 1 equals 2. How many elements here?
2.
And here?
4.
2 to the power 4. to the power 2 equals 4. So it's not a coincidence. And indeed, this power set is closely connected to this power. So, and our last set construction principle is the union. I will give it in some simpler form, less general than it is usually used in mathematics. I say that for every sets A and B, there exists a set which is called A union B or A join B, such that for each x is an element of this union if and only if this object is well familiar to you. When x is an element of the union of A and B.
It belongs to A and belongs to B.
No, not and.
Or
It either belongs to A or to B. So this is usually illustrated by your well-known Euler's diagrams. And what would be more generally? Let's say some words about it and then forget about it. More generally, you will consider the union of a set X. The union of a set X. What does it mean? That means that for each Y, this union is denoted the following way: union of X. Now, union is a unary operation. For each Y is an element of the union if and only if there exists some A, so that Y is an element of A and A is an element of X. So the union is the set of all elements of X. So this way, the union of just two sets might be obtained the following way: the union of this set. This set might be constructed using our fourth principle, and this one is our new principle, union. So Y is an element of the union of X if and only if Y is an element of some element of X. Is it clear? Elements of my elements.
Yeah.
But we don't like it because it is too abstract for us. It is too abstract. So let's stick to this one, to union of these two sets. Using these principles, we may start constructing our usual theory of operations over sets. Let's begin this process, and we shall continue it next time. We don't need new principles at this stage. We may apply the existing ones. What is the intersection or the meet of two sets? The intersection or meet of A and B. What is it? It is a set of common elements. How is it possible to formally define it?
Mhm.
Every
It
X
is
that
a
belongs
set
to
of,
A belongs to B.
but how is it possible to do it formally? That is using our set construction principles.
It sets X from X from A such that X.
That's it. That's it. You may just take all elements from A that belongs to B. That belongs to B. So by definition, you may do it this way. And our lemma says that X, for each X belongs to the intersection if and only if X belongs to A and X belongs to B. It is, of course, very easy to notice. Is it clear?
Yes.
Should I prove it explicitly?
Probably not.
What does it mean that X belongs to this one? That means exactly that. X belongs to A and also X belongs to B. Let's come back to the definition. This is the set of all elements which belong to A and also satisfy phi. So belongs to A in this case, and also belong to B. As a corollary, I may say that A intersection B equals B intersection A. Why is it so? It's easy to prove it. If X is an element of this set, this is equivalent to this conjunction. While here, I have X belongs to B and X belongs to A. And these two are equivalent for logical reasons. Is it clear?
Yes.
Besides the intersection, I have the following set difference, or set minus, A minus B. A minus B. What is it? How is it possible to define the difference?
It's X belongs to A such that
All
X,
x's from A such
but
that
not
X
from B.
is not an element of B. It is quite clear. If we use your favorite diagrams, here we have the intersection. And where is the difference? A minus B. Here it is. Is it clear?
Yes, it's clear.
Another useful term. We say that A intersects we will end our lecture in a minute. A intersects B. That means that the intersection is not empty. They have at least one common element. And dually A and B are disjoint. In Russian we would say simply не пересекаются, disjoint. And in English we have the standard term disjoint. if the intersection is empty. They have no common element. Is it clear?
But if A is an empty set and B is an empty set, the
Then
intersection-
they are disjoint. They have no common element.
okay.
The empty set and A are disjoint for every A. And our last statement is also trivial. Let's call it lemma 6. For all A and B, we say that the intersection of A and B is a subset of A, while A is a subset of the union. And surely the same for B. This is from logic. Of course, if X is an element of A and X is an element of B, then of course X is an element of A. And if X is an element of A, then X is an element of A or X is an element of B. This corresponds to the following tautologies, to the following implications, which are always true. If alpha and beta, then alpha. If alpha, then alpha or beta. Is it clear?
Yes.
And the last statement is about set minus. A minus B is a subset of A, and it is disjoint from B. Is this too clear?
Yes.
So this was the last statement in our today's lecture, and as an exercise which we will solve next time, I suggest you prove the following. A is a subset of B if and only if the intersection equals A. It's very useful. A is a subset of B if and only if the intersection equals the lesser set. So please try it. Try prove it formally.
Sorry, didn't we already have lemma 6 previously?
Where?
Um, upper.
Okay.
Yes, isn't it 6?
Yes, like it should be the same one.
Well, thank you. Let it be lemma 7. So any questions, please?
No, I think no, yes.
So, dear students, to summarize, our subject today was abstract, but it was easy. Easy but abstract. What is the main idea? Please play by rules. Use axioms and definitions. Do not use your imagination too much. Use the rules, axioms, and definitions. Trust me, this is quite important in mathematics. Your ability to play by rules.
Excuse me, I have a question.
So please.
Axiom of foundation. Can you
The
scroll
axiom
to it?
of foundation, okay.
Yeah.
Let's scroll to it. Where is it? Even upper. So
Why is it true? Like why
why
there
is it true? It's true just because we want it to be true. But maybe for that reason, it's called an axiom, not a theorem. we just don't want to have such strange objects, sets that are elements of themselves. In fact, you may consider such sets. You may add them to the universe of mathematical objects. It is possible, and it would not cause any contradiction. But they are counterintuitive. Such sets are counterintuitive. We just don't like them. By the way, please notice that this axiom does not contradict to infinite sequences of set inclusion.
Yeah, but why these signs are different?
Why they are different? In fact, that's a very good question. In fact, we shall have a dedicated exercise about that at our seminar. But rough and ready, why they are not the same? Okay, let's consider any singleton. Let it be, say, singleton of natural numbers. Clearly, n is an element of this set by the definition of singleton.
But singleton is, as I understood, a set of one element.
Of course. Singleton is derived from single, so it has a single element. Okay. N is an element of this set, but n is not a subset of this set. Why is it so? If n is a if n were the subset of this set, then for each natural number x, x would be an element of this singleton. What does it mean? That means that every natural number would be the set of natural numbers. So that would mean that, say, 12 is a set of all natural numbers.
Oh.
Which is quite strange.
Yes.
And at our seminar, we are going to prove that neither this one implies this one, nor this one implies this one, no, this one implies this one, and so on.
But what's the difference? It's like the point.
What is the point? It's another very good question. If you take a plane,
No, it wasn't
the point of some argument, not of the plane.
I mean, what's the difference between these signs?
This one and this one.
Yes, I don't quite get it.
You know, this one is primitive. It is not defined. One set might be an element of another one. And this one is defined. X is a subset of y, if and only if for each z. If z is an element of x, then z is an element of y. This is defined using this one. What is the difference? We may give an example when one relation holds and another one does not. What else? Let's give another example. The empty set is a subset of any set. Do you agree?
Yes.
But the empty set has no element. Neither the empty set has an element of is an element of itself. So they must be distinct, these two relations.
And if we say n belongs to singleton of n, what do we mean? That an element n belongs to that singleton?
Yes. This set is an element of this one. This set is an element of this one. Remember, dear students, there is no such category of objects as elements, but every set might be an element of another one.
So singleton can be also a set inside?
Of course, everything is a set. There are no objects other than sets. This is the main idea. You know, in the high school, you probably used to look at sets as some collections of points or elements, but in fact there is no such thing as element in general, but just an element of some set. Elementhood is a relation between sets. One set is an element of another one. This way, you can model your mathematical objects using sets. If you looked upon them this way, where you have points and sets as geometrical figures, this way it is not enough to model anything interesting.
And then what's the difference between set and a singleton?
Not every set is a singleton, but a singleton is a set of some special kind.
But why
By
not? Sorry, but why not every set is a singleton if we can make every like every elements of a set can be made into another set, and then we have set of a set, and then it is a singleton, isn't it?
Let's consider this set. Is it possible to do so? The set of two sets, it is obtained by this model. Is it possible?
I guess we can do a singleton of that set of
Of course. But the question was, why not every set is a singleton? Assume that this set is a singleton. What does it mean? Clearly, the empty set is an element of this set. Do you agree?
Yes.
Yeah.
Equal sets have the same elements. So the empty set should be the element of this singleton. Likewise, the singleton of the empty set must be an element of this set. You know, for each x is an element of the singleton if and only if x equals a. Is it clear?
Yes.
This is by definition. So that means that the empty set equals a, and that means that the singleton of the empty set equals a as well. By our lemma 2, it should be z. Okay. You know that the empty set is an element of this singleton. Two equal sets have the same elements, so it would mean that the empty set is an element of the empty set, which is not true, as the empty set has no element. So not every set is a singleton. How did I find this set, a set which is not a singleton? Easily. I just took two distinct sets, two sets which are not equal, and then grouped them together.
Mhm.
This can't be a singleton.
Yeah. But how can we say that n belongs to a singleton of n if, like,
According to this definition, every x belongs to the singleton if and only if x belongs to A.
yes.
Just substitute A for x. Then you will see that A is an element of the singleton if and only if A equals A. But this is true.
Mhm, mhm.
Hence, this one is true as well.
So when we said that n belongs to a singleton of n, we meant that n, which is in the left, is like the set of all integer numbers.
N is a set of all natural numbers, but it is an element of another set, namely the singleton. For every set, you may construct a set which contain our initial set, which contains our initial set as an element, namely the singleton.
Mhm.
Can you go back to the axiom of foundation once more, please?
The axiom of foundation, okay.
Well, aren't xn plus 1, xn, and etc. are distinct sets?
It is not necessary.
So axiom tells that we can't have infinite sequence of sets?
Infinite sequence decreasing in this relation. For example, you may easily construct an infinite increasing sequence. For example, let's start from the empty set. It is an element of its singleton. It is an element of the singleton of the singleton, and so on. But no infinite decreasing sequence. It grows to the left. Is it clear?
Yes. But then, like, we have sequence of nested segments in other.
Clearly you have, but here we have not element, not elementhood, but inclusion.
Ah,
But inclusion, of course. This segment includes this one, which includes this one, and so on, infinitely.
so the only difference is that for one we have definition and for other we don't have.
Of course, but the difference not only the fact that you have a definition for this symbol and no definition for this one. The definition itself matters. What is the definition for inclusion? Inclusion is defined in terms of elementhood. So elementhood is a primitive relation. You cannot define everything in terms of some other. Is it clear? In order to
Yeah.
define a notion, you need another notion. But if you want to start from scratch, from the very beginning, you should something you don't define explicitly in terms of something else. So you don't define what elementhood is, but just impose some requirements, some axioms on it. For example, you say that there is no such the infinite decreasing sequence,
Ah, okay, yeah, I see.
and so on. This is known as axiomatic method. Axiomatic method. So you don't say what it is, but just how it behaves. It is very similar to our approach to strings. We did not define these objects, but just impose some axioms. Say x column s equals y column t if and only if you know x equals y and s equals t.
Okay.
So this is the axiomatic method. It is widespread.
Thank you.
Thank you. Any more questions?
No, I don't have.
If
Thank
you have any questions, so please don't hesitate to post it to our group in Telegram.
Okay. Thank you very much.
Thank
Goodbye.
you. Thank you, dear students. Goodbye.
Mm.